Hello and welcome to High Availability MySQL with StorageOS. Let's start with the presentation and the demo of how we install MySQL and how we do high availability in Kubernetes cluster using StorageOS. First, let me show you. We have four nodes in our Kubernetes cluster, and we have StorageOS installed as well in the kube system namespace. You can see we have the 4 daemon sets, 1 instance per node. Also, we have the storage class called fast and StorageOS-replicated that are using the StorageOS provisioner. That will allow us to connect Kubernetes with StorageOS. Today, we're going to use a few YAMLs that are available in GitHub. Everything is completely public, so you can go and check it out. You can see also the reference at the end of the presentation, at the end of the demo. And today, we're going to install MySQL. The first thing to keep in mind is that we're going to use a stateful set, and I'm going to show you in a few seconds how does it look like. First, we're going to create the resources, and now we're going to have a look at the stateful set. There are other resources, other YAMLs, but this one could be the most important one. The first thing to check on the stateful set, or the first thing to know, is that a stateful set is a Kubernetes controller that will enforce, in our case, to have one instance of a MySQL running. We're using a standard default image of MySQL, so it's completely agnostic or anything baked in, and we are mounting a volume in barley MySQL. Obviously, it's where MySQL writes data. Where this volume is coming from is from a volume claim template. Happens to be that the volume claim template is a way to create persistent volume claims that attach to specific pods. We're using the StorageOS replicated storage class, and that will connect to StorageOS, and we will use StorageOS volumes. So we have the MySQL pod running. Now we can check the persistent volume claim that is associated to it. And finally, we can check the persistent volume that StorageOS dynamically provisions. We can see that the claim is, as we were saying, the data MySQL, and the persistent volume claim are all provisioned or handled by StorageOS with Kubernetes and giving the volume or the block device to MySQL. StorageOS runs a service that connects to all daemon sets, and that service will allow us to connect to the StorageOS user interface. I'm doing a port forward in my machine, so we can see in the port 5705, which is the StorageOS API port, that we can access the StorageOS user interface. We can see here that there are the 4 nodes that we mentioned before, and a bit of information that you can check with more detail. Happens to be that StorageOS maps the namespaces of the persistent volume claims to StorageOS namespace, and we can see the 5 GB provision volume coming from the persistent volume claim of MySQL. We can see as well that the replication target is 1, meaning there is 1 primary volume where StorageOS executes the input-output operations, and a replica, meaning 2 copies of the data always in sync. One of the nodes, or the node where the data is hosted, is the RxV7, and happens to be that the replica is in a different node. StorageOS enforces that all instances of the data are always in a different node. Now, let's go and see that we can use StorageOS to start our MySQL anywhere in the cluster. So it happens to be that now the data and the pod are running into different nodes, and you can see that the StorageOS can just present the device to that pod. However, we're gonna go have a look into the data, and then we're gonna move this pod to a different node and see that actually we can access without any problem the same data. StorageOS, you can see here that StorageOS mounts a volume or gives the kubelet a volume to mount into barley MySQL, where we have the MySQL files. Now let's check where that pod is running, and let's cordon this node. We will make sure that no pods can be allocated or scheduled in this specific node, and now we can go and delete the pod. When we do this, the pod is forced to start in a different node completely. Now that the pod is deleted, let's check where the new pod is starting. Remember, this stateful set Kubernetes is enforcing one instance being always running. Therefore, when we delete that pod, it has to start, and because the node was cordoned, it's starting a different node. Now, the pod where is running, the node where the pod is running happens to be the same where the data is, and this is best for performance, so the latency is minimized, so there is less access to the network, and therefore performance for database is as fast as possible. We can enforce with the StorageOS scheduler this behavior by default that will guarantee or will do the best effort to schedule a pod and influence the Kubernetes scheduler to schedule the pod in the node where the primary volume of StorageOS is located for that specific application, of course. We can see that the same data in Barley MySQL is available, and now we can see that the data hasn't moved whatsoever. We move the application starts real fast, whether the data doesn't move that fast. So now we can see that the pod is mounted in the same node that the data is located. StorageOS handles everything internally, all the access through the network. StorageOS has a proprietary protocol internally that allows this capacity. And what actually the MySQL sees internally is just a file system. It doesn't see anything else. So we can do this as many times as we want. We're going to uncordon the first node, cordon the node where now the data is running, where the data, where the pod is scheduled, so where the data is mounted from, and we're going to do the exact same procedure. We're going to start the pod in a different complete node. Once again, we can see that the pod is starting in a different node. In this case, we can see the FNPC, which is a different node from any of the ones that we saw before. Now we can see at the StorageOS user interface that in fact, that's the case. It's the data is in one node, the pod is being created in a different node, and it's mounting the volume. Once again, we can check the contents of that MySQL directory to actually see that the data is just the same files, etc. StorageOS enforces synchronous replication, and that will allow us to fail a node and automatically recover from a failure. Now, let's go and do the most interesting test, which is let's go and shoot the node that actually is holding the data, the primary volume. You can see that the FNPC is where the replica is located. So let's go into the SSH of that node and reboot it. I'm just going to type a reboot and in that specific shell and just stop the node. That was fast enough. Now let's go back and see how the data or where the data is now being served from and where the writes are going to. Specifically, we can see that now FNPC is where the node, the primary, let's just refresh just in case, but now we can see that node FNPC, that was a replica before, now is a primary. We automatically failed over a volume, and actually StorageOS has created a new replica, the 50 in a different node, in the 50 JW, and obviously because there is a small volume and there is no data, StorageOS uses thin provisioning, there is a really fast sync. Now let's check, and actually we can see that the MySQL pod itself didn't restart, didn't see any downtime. The files are just there. So StorageOS has moved where the data is being written to and read from without the application being able to see anything. Of course, if there are hundreds of writes or transactions per second, there is going to be maybe a couple of milliseconds or a couple of 100 milliseconds of a wait to be able to fail over the volume. We can see that the node is in offline. StorageOS has its own health checks. However, StorageOS has moved the volumes. Now the primaries were we can see in the 1/0 where is the primary, and the 0/1 where the replica is located. In the volume, in the node that is offline, we had the primary before. Now we have failed over the replica. It become a primary in the node FNPC, and we have one new replica sync and ready to be working. How does that work? How is that possible? Well, StorageOS implements replication for high availability and automatic failover. So when an application writes towards StorageOS volume that is replicated, StorageOS automatically sends that write in parallel, and when everything is acknowledged, it goes back to the application. So in the case that the node goes down, the StorageOS can automatically fail over the volume and create a new replica. Now, where we can see documentation, how I install StorageOS, where are the examples of the YAMLs that we use for this specific demo, and also which playground environment can we use, which is play.storageos.com. Well, we hope you enjoy the demonstration and get some insights now. We're going to pass to the Q&A and answer some questions from you guys. I have here Paul that will assist me on his gathering all the questions and everything. So actually, my colleague will give me some of the questions that came around from the chat.
Thank you, Ferran. So yeah, some questions for us. The demo shows MySQL running in Kubernetes. Are customers really doing this in production?
Indeed, we have customers running databases in production for sure. Actually StorageOS enables them to move not only the stateless applications and the stateless workloads, but also stateful applications. So they started using StorageOS, they started using stateful workloads such as MySQL, Postgres, also other sort of key value stores or databases or such as Redis or Couchbase or other stateful workloads that are based on queues and message buses like Kafka or indexes like Elasticsearch. Actually, we are leveraging the use of the orchestrator itself, the use of Kubernetes, to give us the capacity to start and stop applications, and because containers start real fast anywhere, but giving all the persistence that these applications need, leveraging StorageOS for the high availability and the production grade storage.
Sounds good. You mentioned in the demo that you used StorageOS replication with MySQL. So a follow-on question to that, should I always use StorageOS replication with my production volumes?
That's a really good question. In fact, what StorageOS replication gives you is active-passive failover, pretty much. So in case of failure, your data is accessible almost immediately. So you don't have downtime on your application. Of course, if the container has to restart in different nodes, you can have maybe a couple of seconds of failover. However, there is another way of seeing this, which is based on MySQL replication. And this happens not only with MySQL, but also with other applications that have replication. For instance, Kafka has a replication factor as well on their partition or topics, different partitions replicated. So in case of MySQL, when you replicate, you can add read replicas. But for active passive, for failovers, I would always recommend to use the StorageOS failover because it's automatic and it's underneath the MySQL file system, so it's at the block device level. When you have to increase throughput with read replicas, yes, add those replicas. So you can actually have a mixed topology where you can take advantage of the best of both cases. So for production, we recommend always to use at least one replica, meaning 2 instances of the data, 2 in-sync copies of the data. Keep in mind, for instance, that most applications implement asynchronous replication. That, in the MySQL case, is using the transaction log. And that means that you can have 1 second, but also 1 minute or even more of delay in between the data you have in the primary and its replicas. If you have to fail over, and it's actually a manual operation in MySQL, and you want to promote that replica, you will have quite significant downtime, and you cannot guarantee that the data is actually the same as you wrote before. So synchronous replication is very important for active-passive model. In this case, StorageOS is giving you that. We could keep talking about this for a long time. Every application is a world and has its own details. So I would say that it depends. It depends on the application.
It depends. Those trustworthy engineering words.
Indeed.
So a final question about backups. Deploying MySQL on StorageOS sounds great, but how can I back up my databases? It's a very important data operation.
Yeah, indeed. Disaster recovery, backups, and snapshots are really important or really common topics that come up, and actually quite frequently. There are two paths to achieve disaster recovery and to achieve backups. One is using tools that are already there for our data. For instance, in Kubernetes, you can use Velero and Restic. By the way, we are doing a demo on Thursday, which we will show how to back up StorageOS volumes using Velero. And the other way of doing it is by using the database backup solutions. Every database is different in the way that it stores data, but also in the way that backups are ensured. To achieve highest consistency or to achieve portability of those backups to other clusters, etc., I would recommend to use the backup tools for every specific database. For instance, you can use MySQL DOM or XDB backup. With MySQL, yeah, there are some options that are blocking for database, so you would have to do it at low peak times. And actually, Kubernetes gives you the tools to set up cron jobs that are distributed and agnostic from the node itself. So you can actually easily set up those backups as well. Elasticsearch, for instance, could use the snapshots, and you need the snapshot repository, right? So that is actually a really good way of backing up Elasticsearch rather than doing the Velero. Yet the Velero is also very useful. So we're going to show that use case as well for Kubernetes users.
That's great. Thank you very much. Well, there are no further questions, so we'd like to thank you all for attending. And please tune in for our next set of webinars tomorrow.
Thank you. Goodbye.